Hello everyone. Today we are going to discuss two of the most fundamental concepts in mechanical and structural engineering, stress and strain. These two quantities are extremely important whenever we are trying to understand how a component behaves under loading. Hello everyone. Today we are going to discuss two of the most fundamental concepts in mechanical and structural engineering, stress and strain. These two quantities are extremely important whenever we are trying to understand how a component behaves under loading. Whether we are designing a simple metal bracket, a vehicle chassis component, a suspension part, or a complex structure, we ultimately want to know how much load it can withstand and how much it will deform. We also want to know whether the deformation is temporary or permanent, and most importantly, whether the component will survive its intended operating life. Stress and strain help us answer these questions. Stress tells us how much internal force is being carried by a particular area of the material. Strain tells us how much the material deforms relative to its original size. Keep this simple idea in mind: load causes deformation, and stress and strain describe what happens inside the material. Let's start with stress. On this page, we can see a simple tensile test performed on a metal specimen. On the left, we have the original specimen. In the middle, the specimen has been loaded and has started to deform, including the formation of a necked region. On the right, the specimen has finally fractured. This simple tensile test helps us understand the relationship between load, stress, strain, and failure. Stress is represented by the Greek letter sigma. The simplest way to think about stress is that it is force distributed over an area. The unit of stress is commonly ampere or megapascals. If a force is applied to a metal coupon, the effect depends not only on the force but also on the area over which it acts. If the force is large, we might expect high stress. But if the same force is distributed over a larger area, the stress will be lower. Now let's look at the equation. We have a simple cylinder with a force F acting on it, and the cross-sectional area is represented by A. The stress is calculated as sigma equals F divided by A. So stress is simply the applied force divided by the cross-sectional area. Suppose we have a force of 10,000 newtons acting on an area of 1,000 square millimeters. The stress would be 10 newtons per square millimeter or 10 MPa. Now the important engineering question is, how can we reduce the stress? According to this equation, there are two basic possibilities. Number one, reduce the force. Number two, increase the area. If we cannot reduce the applied load, one straightforward way to reduce stress is to increase the cross-sectional area. Imagine two components carrying exactly the same force. The component with a larger diameter has a larger cross-sectional area, so the same force is distributed over more material. Therefore, the stress is lower. This simple concept has a major consequence in engineering design. If we keep increasing the size, we can reduce stress. But in real engineering design, things are not that simple. Increasing the cross-sectional area also increases the amount of material. That means the component becomes heavier and more expensive. In automotive and aerospace applications, unnecessary weight can also reduce overall energy efficiency. So we cannot simply design every component to be extremely large. We need to find an optimum design D strong enough for the reloading environment, but without unnecessary material. This is one reason lightweighting is so important. We want the component to survive its intended loading while keeping weight and cost under control. Accurate knowledge of the actual loads is therefore extremely important. If the assumed loads are much higher than the real loads, we may end up with an unnecessarily heavy design. Now there is another challenge. What happens if the component is not a simple cylinder? What happens if the designer changes the geometry? Here we have a component with a reduced section in the middle. Someone might say that we already increased the size, so the stress should be low. But the middle section has been necked down. That means the effective cross-sectional area in that region is smaller. Since our basic equation is sigma equals F divided by A, if the effective area decreases, the local stress increases. There is also another effect. The sudden change in geometry creates what we call a stress concentration. Even if the average stress calculated using force divided by area appears acceptable, the local stress near the geometric discontinuity can be much higher. This happens in real components around holes, sharp corners, notches, grooves, abrupt thickness changes, and other sudden geometry changes. These locations can become critical locations for fatigue failure. Now let's move from stress to the second important quantity, strain. Imagine that we apply a tensile force to this metal cylinder. The cylinder becomes slightly longer. The amount by which it becomes longer is the change in length. Strain tells us how large that change is compared with the original length. On this page, we can see the original cylinder and the elongated cylinder. The original length is represented by L0 and the change in length is delta L. Strain is defined as epsilon equals delta L divided by L0. So strain is the change in length divided by the original length. Both the numerator and denominator have units of length such as millimeters. Therefore, the units cancel out and strain is dimensionless. Because the actual deformation is often extremely small, engineers commonly use microstrain. One example is a strain value of 0.050. That value can be written as 50 microstrain. This is especially useful when measuring strain experimentally using strain gauges. Now we have two important quantities. Stress tells us about force intensity inside the material, while strain tells us about deformation. The next question is, how are stress and strain related to each other? That is where the stress strain curve becomes very important. On this page, we see a stress versus strain graph. The vertical axis represents stress, sigma, and the horizontal axis represents strain, epsilon. At the beginning of loading, the relationship between stress and strain is approximately linear. This is called the elastic region. The word elastic is very important. If the material remains within this region and we remove the load, the component returns to its original shape. The slope of the straight line portion of the stress-strain curve is called Young's modulus, represented by E. The relationship is sigma equals E times epsilon. We can also write E equals change in stress divided by change in strain. Young's modulus tells us how much stress is required to produce a certain amount of strain in the elastic region. A material with a higher Young's modulus is generally stiffer, while a material with a lower Young's modulus is generally more compliant. This linear relationship is commonly referred to as Hooke's law. But what happens if we keep increasing the load? Eventually, the material reaches a point where the stress-strain relationship is no longer linear. This takes us into plastic behavior. This page shows the complete stress-strain curve. At the beginning, we have the linear elastic region, and then we approach the yield strength. The yield strength represents the point beyond which the material begins to exhibit plastic deformation. In reality, the transition from elastic to plastic behavior is not perfectly instantaneous. There is a small transition region. Therefore, the commonly used 0.2% offset method is used to define yield strength. We take the elastic line and construct an offset line corresponding to 0.2% strain. Where this line intersects the stress-strain curve gives the conventional yield strength. Once the material enters the plastic region, the deformation becomes permanent. If we remove the load, the component will not completely return to its original shape. If we continue increasing the load, eventually we reach the ultimate strength. After this point, the specimen enters the necking region. The cross-sectional area starts reducing significantly in a localized region. Eventually, the material fractures. So from left to right, we have elastic deformation, yielding, plastic deformation, ultimate strength, necking, and finally fracture. This curve is extremely important for understanding material behavior. But there is another distinction: we need to understand engineering stress versus true stress. Now let's look more carefully at what happens to the cross-sectional area as the specimen is loaded. Initially, the specimen has an original cross-sectional area represented by A0. As we apply more load, the specimen deforms. During tensile loading, the cross-sectional area changes. Especially during necking, the local area becomes significantly smaller. Engineering stress does not account for this changing area. Engineering stress is calculated using the original cross-sectional area. So conceptually, engineering stress equals force divided by the original area. This makes engineering stress relatively simple to calculate, but it does not represent the actual instantaneous stress once the geometry has changed significantly. True stress takes the change in area into account, so true stress equals force divided by the actual instantaneous area. Look at the sequence of images. Initially, we have the original specimen. Then it deforms, plastic deformation and necking become more pronounced, and finally the specimen fractures. The cross-sectional area is continuously changing throughout this process. Therefore, using the actual area becomes important when we want to understand large deformation behavior. Now let's compare the two curves directly on the final page. Here we can see two curves on the same stress-strain graph. The red curve represents engineering stress and the blue curve represents true stress. Remember, engineering stress uses the original cross-sectional area, while true stress uses the actual instantaneous cross-sectional area. As the specimen continues to deform, the actual area decreases. Therefore, the actual stress in the material can continue to increase. This is why the true stress curve continues upward, while the engineering stress curve appears to decrease after the ultimate strength. However, the engineering stress curve is often more convenient for identifying features such as ultimate tensile strength and the conventional stress-strain behavior. So let's summarize the complete story. We start with an applied load. That load produces stress in the material. The material responds by deforming, and that deformation is described by strain. Initially, stress and strain have a linear relationship. This is the elastic region, and the slope of this region gives us Young's modulus. If we remove the load within the elastic region, the component returns to its original shape. If we continue increasing the load and cross the yield point, the material enters the plastic region. Permanent deformation now occurs. As the load continues to increase, we eventually reach ultimate strength. Then necking begins and eventually the specimen fractures. Because the cross-sectional area changes during deformation, we distinguish between engineering stress, which uses the original area, and true stress, which uses the actual area. Before we finish, let's summarize the key equations and concepts. First, stress is force divided by area. Sigma equals F divided by A for the same force. Increasing the area reduces the stress. Second, strain is change in length divided by original length epsilon equals delta divided by 0. Strain is dimensionless and is often expressed in microstrain. Third, in the elastic region, stress and strain have a linear relationship sigma equals E times epsilon, where E is Young's modulus. These concepts form the foundation for understanding nonlinear FEA, fatigue, durability, strain, life analysis, and failure prediction. Thank you.